Welcome to this explainer. Today we're unraveling a truly fascinating chemical mystery. It starts with a simple reaction in a basic glass test tube, but it quickly scales up to explain the very biology of the world around us. We're looking at a phenomenon known as the royal blue transition, which is a perfect, visually stunning example of coordination chemistry in action. So, if you've ever wondered how elements interact at the atomic level to create entirely new, vibrant substances, you're in exactly the right place. Let's dive right in.
We're kicking things off with a simple question to spark our curiosity. How does a basic pale liquid suddenly transform into a vivid, deep royal blue? I know, it sounds a bit like a parlor magic trick, but it's pure observable science, governed by the strict rules of electron exchange. This dramatic color change is our entry point today. It's the visual hook proving that something profound and structurally complex is happening at the microscopic level, completely changing how this liquid interacts with light.
Okay, to figure this out, we need to set up our lab safely. We're gathering our primary chemicals, a standard copper sulphate solution. That's what gives us that initial pale watery blue, and our ammonia solution, which is going to act as our active agent. Now, safety is absolutely paramount here. We've got our gloves and safety goggles on, and because ammonia vapors are famously sharp and strong, we're making sure our workspace is well ventilated. Clean test tubes and a precise dropper in hand, we are officially ready to play molecular detectives.
Let's walk through the physical steps of this activity. It's a straightforward procedure, but we need precise execution to actually catch the intermediate states. First up, we start by adding a small quantity of our pale copper sulphate solution to a clean test tube. Next, we carefully introduce just 2 to 3 tiny drops of the ammonia solution. And finally, the big moment. We flood the system by adding excess ammonia while giving the test tube a gentle shake. Just 3 simple actions, but they're about to trigger a wild cascade of chemical events.
Now that first reaction we see, that's where things get super interesting. When we execute that second step, adding just those few tiny drops of ammonia to the light blue copper sulphate, the solution doesn't just change its tint. No, it fundamentally changes its state. We get this sudden formation of a cloudy, chunky, light blue precipitate. The clear liquid is just gone, replaced by this dense solid forming right inside the test tube, which chemists identify as copper hydroxide.
But here's where the mystery literally deepens. As we move to step 3 and add that excess splash of ammonia with a gentle shake, the cloudy precipitate we just created vanishes completely. It dissolves right before our eyes, leaving behind a perfectly clear fluid once again. Which brings us to our next big logical question. Why? Where on earth did that solid copper hydroxide go, and what kind of molecular architecture took its place to force it back into a liquid state?
And this highlights the stark contrast of our macro-level mystery. We just witnessed a sudden, dramatic shift from a cloudy, light blue solid substance into a perfectly clear, incredibly intense, deep royal blue solution. Its physical appearance and its optical properties have totally transformed. To really understand why that chunkiness dissolved and birthed this breathtaking new color, we have to look closer. We literally have to zoom in and analyze the fundamental interactions happening between the individual atoms and molecules in that tube. To solve this puzzle, we're diving into the microscopic level to introduce a crucial player in advanced chemistry, the ligand. Think of ligands as very generous molecules, or ions. They're fully equipped with lone pairs of electrons that they are more than willing to donate. They actively seek out a highly charged metallic partner, using those donated electrons to form a highly stable, structured coordination bond with a transition metal ion. It's not your standard ionic or covalent bond, it's a very specific type of partnership that builds much larger, complex molecular geometries.
So, the crucial takeaway here is that these electron-donating ligands bond to a central metal ion hub, creating what chemists call a coordination complex. Picture it like a central hub on a wheel, with precise geometric spokes reaching out to connect with surrounding partners. The transition metal ion sits squarely in the middle, catching those electron pairs, while multiple ligands surround it. They coordinate their positions perfectly, donating their electrons to lock the entire intricate structure together into a very specific 3D shape.
Let's map these definitions directly onto our royal blue mystery. Our central hub, the central metal ion, is the copper ion from our initial copper sulphate. Its entire job in this environment is just to sit there and receive electrons. On the flip side, playing the critical role of the ligand, we have the ammonia molecules. Their job is to donate those lone pairs of nitrogen electrons straight to the copper. Remember when we added excess ammonia in step 3? We essentially flooded the environment, providing enough ligands to completely surround the copper and build a brand new, highly stable structure.
All of this chemical matchmaking builds to our final identity, the tetraammine copper-2 ion.
Represented by the formula CuNH34 with a 2+ charge, this shows us exactly what happened down at the atomic level. 4 separate ammonia molecules have formed a stable new geometric alliance with one single copper ion hub. Now, this specific arrangement actually alters the energy levels of the copper's electrons, and because of those shifted energy levels, the complex absorbs certain wavelengths of light and reflects others. The result? That intense, signature, deep blue color that our eyes perceive.
Once you grasp this mechanism, it opens up a really fun world of predictive science. Seriously, it's fascinating to consider how changing the characters in this micro-narrative would completely change the ending. For instance, what if we swapped out the ammonia ligands and threw in chloride ions instead? Because the specific ligand dictates the shape and the electronic energy of the complex, substituting chloride completely alters the resulting coordination complex. In fact, if you use chloride, the solution turns a distinct, bright yellow-green. The metal is exactly the same, but changing the ligand changes the whole shebang.
Section 3. The wisdom of coordination chemistry, from the test tube to the real world. We've successfully solved the chemical mystery of the dissolving precipitate and the changing colors, but let's zoom back out. Because this micro-level coordination chemistry isn't just a neat visual trick to do in a lab, it fundamentally shapes the macro world around us.
The exact same principles we just observed, a central metal ion surrounded by electron-donating ligands, governs some absolutely essential real-world applications. In medicine, scientists use coordination complexes to design highly specific treatments. The famous chemotherapy drug cisplatin, for example, is actually a coordination complex centered around platinum. In industry, these complexes act as incredibly powerful catalysts, speeding up manufacturing processes for plastics and fuels. And in broader science, they are the backbone of advancing analytical chemistry, helping us detect heavy metals or extract specific substances with incredible precision.
But even more amazingly, these exact types of coordination complexes are the engines behind massive biological marvels. Have you ever stopped to wonder why our blood is red? It's literally because of hemoglobin, which is a massive, intricate coordination complex with a central iron ion. And why are leaves green? Because of chlorophyll, another brilliant complex, but this time with a magnesium ion acting as the hub. The vibrant colors of life itself and the very respiration of our planet are driven by the exact same ligand-to-metal bonding mechanics we just created in a tiny glass tube. How cool is that?
Ultimately, understanding these invisible molecular alliances is what empowers scientists so tremendously. It allows us to explain the colorful, dynamic, and complex world around us. But it's way more than just explaining it. It allows us to actively design groundbreaking, useful materials across medicine, heavy industry, and environmental science. By mastering how to snap these molecular building blocks together, picking the right metal and the perfect ligands, we can literally build customized molecular solutions for the future.
I'll leave you with this final thought to explore on your own. As you go about your day and observe the environment around you, what other vibrant colors or distinct materials in your daily life are secretly hiding an invisible, complex chemical dance? What metal ions and ligands are silently working together right under your nose to keep the modern world moving? Keep that curiosity alive, and thanks so much for joining me for this explainer.